Welcome back, everybody, to this fun class, AO3. Let's get started. The first thing which we will do is to review a bit what we have learned last time, and then we'll go to the next level to start the coupled oscillators. Okay. So last time we have learned a lot on damped-driven oscillators. So as far as the class has been going, actually we only start a single object, and then we introduce more and more force acting on this object. We introduce damping force. We introduced driving force last time. And we see that the system become more and more difficult to understand because of the added component. But after the class last time, I hope that I convince you that we actually can understand driven oscillators. And there are two very important things we learned last time. The first one is the transient behavior, which is actually a superposition of the homogeneous solution and the steady-state solution. Okay. One very good news is that if you are patient enough, you shake the system continuously, and if you wait long enough, then the homogeneous solution contribution will go away. And what is actually left over is the steady-state solution, which is actually much simpler than what we saw beforehand. It's actually just harmonic oscillation at driving frequency. Also, I hope that you also have learned a very interesting phenomenon, which is resonance. When the driving frequency is close to the natural frequency of the system, okay? Then the system apparently like it, okay? Then you would respond with large amplitude and oscillating up and down at the driving frequency. So that we call it resonance. Okay. So this is actually the equation of motion which we have learned last time. You can see it's a theta double dot plus gamma theta dot is a contribution from the drag force, and omega 0 squared theta is actually contribution from the so-called spring force. And finally, that is actually equal to F0 cosine omega dt, the driving force. And as we mentioned in the beginning, if we prepare this system in the underdamped situation, okay, then the full solution is a superposition of the steady-state solution, which is the left-hand side, the red thing pointing to this steady-state solution. There's no free parameter in the steady-state solution, right? So A, the amplitude, is determined by omega d. Delta, which is the phase, is also determined by omega d. There's no free parameter, okay? And in order to make the solution a full solution, we actually have to add in this homogeneous solution back into this again. And basically, you have B and alpha. Those are the free parameter, which can be determined by the given initial conditions. Okay? So if we go ahead and plot some of the example as a function of time, so the y-axis is actually the amplitude, and the x-axis is actually time, and what is actually plotted here is a combination or the superposition of the steady-state solution and the homogeneous solution. And you can see that there are individual components also shown in this slide. You can see the red thing oscillating up and down harmonically is a steady-state solution contribution, and also you have the blue curves, which is actually decaying away as a function of time. And you can see that if you add these two curves together, you get something rather complicated. you will get some kind of motion like then the homogeneous solution actually dies out. Then what is actually left over is just the steady state solution harmonic oscillation. And in this case, omega d is actually 10 times larger than the natural frequency. Okay? And there's another example which is actually also very interesting, is that if I make the omega d closer to omega 0, okay, in this case, it's actually omega d equal to 2 times of omega 0. Then you can produce some kind of motion, which is like this. So you have the oscillation, and it stays there for a while, then goes back, and oscillate down, and stay there for a while, then goes back, okay? As you can see from there. The homogeneous solution part and the steady state solution part actually work together and produce this kind of strange behavior, okay? And that's actually just another example. And if you wait long enough, again, what is actually left over is the steady state solution, okay? So what are we going to do today? So today, we are going to investigate what will happen if we try to put together multiple objects and also allow them to talk to each other, okay? So if we have two objects and they don't talk to each other, then they are still like single object. They are still like simple harmonic motion on their own. But if you allow them to talk to each other, this is actually so-called a coupled oscillator, then interesting thing will happen, okay? So in general, coupled systems are super, super complicated, okay? So let me give you one example here. This is actually two pendulums. They are coupled to each other. They are actually connected to each other. One pendulum, the second one is here, okay? And for example, I can actually give it an initial velocity and see what is going to happen. You can see that the resulting motion, okay, remember, we are just talking about two pendulums. They are connected to each other, okay? The resulting motion is super complicated, okay? This is actually one of my favorite demonstrations. You can actually stare at this machine whole time. You can see that sometimes it does this rotation, sometimes it doesn't do that, and it's almost like a living creature, right? So we are going to solve this system? No, probably not in else. But as I mentioned before, you can always write down the equation of motion, and you can actually solve it by computer, okay? Maybe some of you, the course 6 people can actually try to write the program to solve this thing and to simulate what is going to happen, okay? So let's take a look at this complicated motion again. So you can see that the good news is that there are only two objects, and you can see, okay, look at the orange dot. The orange dot is actually always moving along a semicircle, okay? But if you focus on the yellow dot, okay, the yellow dot is doing all kinds of different things, okay? It's very hard to predict what is going to happen, okay? So what I want to say is those are very interesting examples of coupled system, but they are actually far more complicated than what we thought because they are not actually small oscillation around equilibrium position, okay? So you can see that now if I stop this machine and just perturb it slightly, giving it a small angle displacement, then you can see that now the motion is much more easier to understand. You see, you actually even get one of these questions in your PSAT. Okay, that's the good news. So our job today is to understand what is going to happen to those coupled oscillators. Let me give you a few examples before we start to work on a specific question. The second example I would like to show you is a saw, and you actually connect it to two, actually a ruler, a metal ruler, which is actually connected to two massive objects. Okay, now I can actually give it the initial velocity and see what happens. And you can see that they do talk to each other through this ruler, this metal ruler. Can you see it? I hope you can see it. Okay, it's a bit small. But it's very interesting that you can see, originally I'm just actually introducing some displacement, in your left-hand side mass. And the left-hand side things start to move also, right, after a while. There are two more examples which I would like to give you, introduce to you. There are two kinds of pendulums which I prepared here. The first one is, there are two pendulums, okay? They are connected to each other by a spring, okay? And if I try to actually introduce displacement, I move the both mass slightly and see what is going to happen. And you will see that the motion is still complicated, although if you stare on one of the objects, it looks more like harmonic oscillation, but not quite. For example, this guy is slowing down, and this is actually moving faster. And now the right-hand side guy is actually moving faster. Motion seems to be complicated. Also, you can also look at this one. Those are the two pendulums. Actually, they are connected to each other by this rod here, okay? And of course, you can displace the mass from the equilibrium position. Oh, not going to hit, not hitting each other. So you can displace the mass from each other, and you can see that they do complicated things as a function of time. Okay, how are we going to understand this? And I hope that by the end of this lecture, you are convinced that you can actually solve this really easy, following a fixed procedure, okay? In those examples, we have two objects that are connected to each other, and therefore they talk to each other and produce a coupled motion, okay? Those are coupled oscillators examples. There's another very interesting example, which is called Wilberforce pendulum. Okay, so this is actually a pendulum. Okay, it can actually rotate like this, and it can also move up and down. It's connected to a spring. Okay, the interesting thing is that if I just start with some rotation, okay, you can see that it starts to also oscillate up and down. You see? So initially, I just introduced a rotation. Okay, now it's actually fully rotating, and now it starts to move up and down. And you can see that the energy stored in the pendulum is actually going back and forth between the gravitational and the gravitational potential, between the potential of the spring, and also between the kinetic energy of upside down, up and down motion, and the rotation. Okay, so they are actually doing all those transition all the time, right? So you can see. So initially, it's actually just rotating, and then it starts to move up and down. And this one is also very similar, but now the mass is much more displaced. And if I try to rotate this system without introducing the horizontal direction displacement, it still does this up and down motion like a simple spring mass system. So what caused this kind of motion? That is because when we move this pendulum up and down, we also slightly unwind the spring that actually can generate some kind of torque to this mass and produce rotation behavior. Okay, and you can see that this is actually involving just one single object, but there's a coupling between the rotation and the horizontal direction motion. Okay, so that's actually also a spatial kind of coupled oscillator. Okay, so after all this, before we get started, I would like to say that what we are going to do is to assume all those things are ideal, okay, without damping force, without driving force. We may introduce that later in the class, but for simplicity, we just stay with just ideal case. Okay, before the math becomes super complicated to solve it in front of you. And also, we can see that all those complicated motion are just illusion, okay? Actually, the reality is that all of those are just superposition of harmonic motions, okay? You will see that by the end of this class. Okay, so that's actually really amazing. Okay, so that's immediately get started. So let's actually take a look at a system together and see if we can actually figure out the motion of this system together. So I have a system with 3 little mass. So there are 3 little mass in this system. They are connected to each other by spring. Those springs are highly idealized springs, and they have spring constant K and the natural length L0, okay? And they are placed on Earth, okay? And I carefully design the lab so that there's no friction between the desk and all those little mass, okay? So once you get started and look at this system, you can imagine that there can be all kinds of different complicated motions, right? You can actually, for example, just move this mass and put all those the other 2 on hold, and they can oscillate like crazy. They can actually do a very similar kind of motion. There are many, many possibilities, okay? But if you stare at this system long enough, okay, you will be able to identify spatial kind of motion, which is actually easier to understand, okay? So what I would like to introduce you is a spatial kind of motion which you can actually identify from the symmetry of this system, okay? So that is actually so-called normal modes. Okay, so what is actually normal mode? A spatial kind of motion we are trying to identify. That is actually the kind of motion which every part of the system, okay, is oscillating at the same frequency and the same phase. Okay, so that is actually so-called the normal modes, and it's actually the kind of spatial kind of motion which I would like you to identify with me. And we will later realize that those spatial kind of motion, which is easier to understand, actually help us to understand the general motion of the system. You will realize later that the most general motion of the system is actually just a superposition of all the identified normal modes. And we are done because we have a general solution already. Okay, so that's actually a very good news. That actually tells us that we can understand the system systematically and step by step. And then we can actually write the general motion of the system as a superposition of all the normal modes. Okay? So let's get started. So can you guess what are the possible normal modes of this system? So that means each part of the system is oscillating at the same frequency and at the same phase. Can anybody and any one of you guess what can happen? Each part of the system oscillating at the same frequency. Yeah. Very good. So he was saying that now I displace the right-hand side two mass all together by a fixed amount, and also the left-hand side, right, by a fixed amount, and let go. Okay? So that's what you're saying, right? Okay, so the first mode we have identified is like this. So you have left-hand side mass, okay, displaced by delta x, and the right-hand side two mass are also displaced by delta x. Okay, so basically you hold this three little mass and stretch it, okay, by the same, introduce the same amplitude to all those three little mass and let go. Okay, so that is actually one possible mode. And if we do this, then basically what you are going to see is that this is actually roughly equal to this system. They are connected to each other by two springs, and the right-hand side part of the system, since both masses are oscillating at the same amplitude at the same phase, they look like as if they are just one single mass with mass equal to 2m. Okay? And if we introduce a displacement of delta x, then what is going to happen is that if I take a look at the mass, the left-hand side mass, and the force acting on this mass, the force will be equal to minus 2k times 2 delta x, right? Because that's actually the amount of stretch you introduce to this spring, right? Okay, and that will give you minus 4k delta x, okay? And we have already solved this kind of problem in the first lecture, right? So therefore, you can actually immediately identify omega, okay? In this case, omega A squared will be equal to 4k divided by 2m, right? This is actually the effective spring constant, and this is actually the mass, right? Okay, so that is actually the frequency of mode A. Okay, can you identify a second kind of motion which does that? So in this case, what is going to happen is that the three mass will, okay, this 1, 2, and 3. The three mass will will oscillate as a function of time like this, with angular frequency of square root of 4k over 2n. What is actually a second possible motion? Yes.
One of the small masses being stretched and the second small mass being
compressed.
Compressed with the same. Yeah.
Very good. I'm very lucky that I'm in front of such a smart cloud today. And we have successfully identified the second mode, mode B. Okay, so what is going to happen is that the left-hand side mass is not moving, right? And you compress the upper one slightly, and you actually stretch the lower one, the lower little mass, to the opposite direction. Okay, the displacement is delta x, and the displacement of the second mass is delta x. Okay, so what is going to happen? What is going to happen is that the left-hand side mass will not move at all, right? Because the force, the spring force is going acting on this mass is going to cancel, right? Okay, and apparently these two little mass is going to be doing harmonic motion, okay? But they are actually, since this left-hand side mass is actually not moving, it's as if this is a wall, and this was a single spring K, and it's actually connected to a little mass. And it actually got displaced by delta x. Okay, so what will happen is that this mass will experience a spring force, which is F equal to minus K delta x. Therefore, we can actually immediately identify omega b squared will be equal to K over m. Okay? So you can actually see that we have identified two kinds of modes, which every part of the system is oscillating at the same frequency and at the same phase. Everybody agree? No, not everybody agree. Look at this guy. This guy is not moving, right? How could this be? This is actually not a normal mode, right? Isn't it? Okay, I hope that wake you up a bit. I can be very tricky here. I can say that this mass is actually also oscillating, but with what amplitude? Zero amplitude, right? So the conclusion is that, everybody is actually oscillating at the same frequency, but this guy is with zero amplitude, okay? Yes.
Are they oscillating at the same phase as well?
Yeah. Oh, very good question. So another objection I received, right? So life is hard for me today. Hey, this guy is actually oscillating out of phase, right? These two guys are out of phase, right? But I can argue that the amplitude of the first mass is actually minus, actually have a minus sign compared to the second mass, okay? Then they are, again, in phase, okay? Okay, so very good. I like those questions. And I hope that I have convinced you that everybody is oscillating, although you cannot see it because the amplitude is small, it's zero. And they are all oscillating at the same phase. Okay? Yes?
How come there's only one mass?
Oh, the right-hand side? Oh, yeah. That is because the left-hand side mass, the 2m1, is actually not moving, right? Because there are two spring forces. One is actually pushing the mass. The other one is pulling the mass. Okay, and they cancel perfectly. Okay, therefore, it's as if those two guys are not, they don't find each other actually, and it's like okay, they are just two mass connected to a wall alone, and you can actually now identify what is actually their frequency. Okay, very good. Okay, so we made a lot of progress from the discussion. And Now I would like to ask you for help. What is actually the third oscillation? Yes.
There is no third normal mode.
There's no third normal mode.
There is no third normal mode because we're restricted to one dimension. And I cannot imagine another motion that will not displace the center of mass.
Yeah, very good. That's very good. So on the other hand, you can also say, I also take the center of mass motion as one of the normal mode. Yeah, I think that's also fair, okay, to do that. Okay, it's very good observation. You can see that the whole system can move simultaneously, right? And they are also I can also argue that they are oscillating at the same frequency, at the same phase, because they are all moving together. So this is the 2m connected to S1, S2, okay? All of them are moving at the same direction, okay? So now I can calculate the force. What is the force? F is 0. Therefore, omega c is 0, okay? So you can actually take the small limit of omega, okay? So of course I can pretend that those masses are connected to a really, really small spring to the wall with a spring constant K prime, and I have K prime goes to 0, and they are actually going to oscillate with omega c goes to 0, okay? So in this case, the amplitude is going to increase forever, right? Because you have basically A sine omega ct, right? And this is actually roughly A omega c t. And this is actually just Vt, right? So what I want to argue is that this is actually also oscillation, but with angular frequency 0. And the general motion can be written as Vt times c, for example, some constant. Okay? Any questions? So what I'm going to do next may amaze you. Very good. So we have identified 3 different kinds of modes. We have mode A, which is actually with omega A squared equal to omega A squared. Where's omega A squared? There. It's 4k over 2m. And also, the motion is like this. x1 equal to A cosine omega A t plus phi a. x2 is equal to A minus A, actually, because they are actually having a different sign, right? So if the motion is actually in the left-hand side direction, then the 2 mass is actually oscillating in the opposite direction, right? So therefore, I get the minus sign in front of A, okay? Cosine omega A t plus phi A. x3 will be also equal to minus A cosine omega A t plus phi A. Of course, I need to define what is x1, x2, and 3, right? That's actually why most of you are got super confused. Okay, so the x1, what I mean is that it's the displacement of the mass 2n. I call it x1. The displacement of the upper mass, the upper little mass, I call it x2. And finally, the displacement of the third mass, I call it x3, right? Therefore, you can see that mode A, you have this kind of motion. Okay, the amplitude of the first mass is A, Therefore, if I define that to be A, then the second and third one, the amplitude will be defined as minus A. And you can see that all of them are oscillating at fixed angular frequency, omega A, omega A, omega A, and also fixed phase, phi A, phi A, phi A. Okay? Of course, we can also write down what we get for mode B, right? For mode B, the left-hand side mass is not moving, stay put, and the other two masses are oscillating at the frequency of omega B, and the amplitude, they actually differ by a minus sign, okay? Omega B squared is equal to K over N from that logical argument. And then actually we get x1 equal to 0 times cosine omega bt plus phi b. X2, I get b cosine omega bt plus phi b. X3, I get minus b cosine omega bt plus phi b. Any questions here? Okay. Finally, mode C. Okay, all the mass x1 is equal to x2 is equal to x3 is equal to C plus Vt. Okay. So you can see that we have identified 3 modes: mode A, mode B, and the mode C. Okay, and there are 3 angular frequencies which we identified for all those normal modes. Okay, omega A, omega B, and omega C. Okay, and you can see that we also identified how many free parameters. 1 free parameter, 2, 3, 4, 5, and 6. So if you are careful, you write down the equation of motion of this system. You will have 3 coupled differential equations. And those are second-order differential equations. If you have 3 variables, 3 second-order differential equations. If you manage it magically with the help from a computer or from math department people, right? How many pre-parameters will you expect in your general solution? Can anybody tell me how many? I have 3 second-order differential equations. Yes? 6, right? So look at what we have done. We identified already 1, 2, 3 normal modes, right? And there are 1, 2, 3, 4, 5, 6 free parameters. That tells me I'm done. Right? I'm done, because what is actually the general solution? The general solution is just a superposition of mode A, mode B, and mode C. You have 6 free parameters to be determined by 6 initial conditions, which I have to tell you what are those initial conditions, okay? So isn't this amazing to you? I didn't actually even solve the differential equation, and I already get the solution, okay? And you can see another lesson we learned from here is that although you can imagine that the motion of this system can be super complicated, this whole thing can do this, all the crazy things all over the place, and the central mass can move, as you said, but the result is actually very easy to understand. It's just 3 kinds of motion: the displacement, and two kinds of simple harmonic motion. We add them together, and then you will get the general description of that system.